now we're going to talk about magnetic flux. So magnetic flux, we said it's not a vector quantity, it is a scalar, right? So it is showing how much basically magnetic field is passing through a certain area. So if you have a certain area like this, if you divide that certain area into small segments, and if you have the knowledge of B, which is the magnetic field, magnetic flux density, and ds, which is basically the vector associated with the differential vector associated with the surface, which is going to be perpendicular to that surface in that specific basically area. So at each of these segments, you have a certain ds, which is perpendicular to that. So if you have the knowledge of B and ds, and then put them through this integral, and find that integral, meaning that, again, that ds, you would make it smaller and smaller and smaller, and that sigma would be converted into an integral, then find out the result that would give you out the magnitude of the flux that is passing through that area. Again, this is useful when you have basically certain shapes that you know how the distribution of your flux density is. So therefore, if the flux density is, for example, constant B, and you have like part of a sphere, for example, where at each point on that sphere, the flux is perpendicular to the surface of that sphere, then your total flux would be Bs, where S is that certain area associated with that sphere, as you can see. So let's go to example 5.1. We have flux calculation. We have the solenoid of figure 5.5. So here was figure 5.5. And we have the current equal to 1 amps, and the cross-sectional area is 4 centimeters squared. We want to find the magnetic flux, which is flowing through the solenoid of 100 turns, assuming a core with average length of 50 centimeters and relative permeability of 5,000, right? So everything is given here. We know that the magnetic flux intensity would be Ni over L. And then once you multiply H by mu, you would get the magnetic flux density. So therefore, B would be equal to mu times Ni over L, where the mu itself would be mu R times mu 0 Ni over L. And phi would be B times S, where S would be the area associated with the cross-section of that solenoid, right? That cross-section has been given out to you at 4 centimeters squared. So you have all of that knowledge. You can just multiply them together and find the flux as 0.5027 milliwebers, right? So if I want to do this in MATLAB, I would go to MATLAB, and MATLAB has a very good environment where you can have live scripts. So those live scripts give you the option to have a combination of both text and equations. In the text, you can describe whatever you're doing. So I'm having my problem here. I can even copy and paste this into the text section, and then we can have the code section here. So everything needs to be clear. So I'm starting, usually, this is a practice that I do. I clear the screen, I clear the environment for every new problem. And if there have been some figures previously in MATLAB, I just close them all. And here I have an input portion, and then a procedure, which goes through the step-by-step procedure, and then an output portion, right? So the inputs to my problem are the current. So that current is equal to 1. And I put, usually it's a good practice to put the units here. And also keep that in mind that I is a special, basically, by default, I and J in MATLAB are considered to be square root of -1, right? So I and J are equal to. So if you do associate another number to them, if you need to use I and J in your calculations, complex calculations, complex number calculations, you can always use one I and one J. So even though I put I equal to 1 here, so if I call I, it won't give me that I or J anymore, but one I always gives me the 0 plus 1J, or 1I, or 1J, same thing. So that's a good practice to just use 1I or 1J during your calculations. So I put I equal to 1, And then what else? I have 4 centimeters squared. That's the cross-sectional area. So S is 4. Again, it's a good practice to basically do everything in terms of SI units. So convert them right away there. So this is centimeters squared. If you want to make it into meters squared, you have to multiply that by 1 e minus 4, right? So that would be 4 e minus 4. And then you can put meters squared here. And then I have n equals to 100 turns. And I have my L, or length, equal to 50 centimeters, or 50 e minus 2 in meters. And permeability, your mu is 5,000. And I have my mu 0. This is mu r, 5,000. And my mu 0 is how much? 4 pi e minus 7. That is in henries per meter. This is basically what we have in here. You can find H equal to N times I over L, and that will be given to you in the SI unit. What is the SI unit of H? Amperes per meter. Your outputs would be the B, which is mu times, your mu becomes mu R times mu 0 times H, which will come as Weber over meters squared, and your phi would be equal to B times S. So let's see what would be output L. Okay, so I got an error. This is small L. Always pay attention to the comment. So the comment, the error that gives you is given to you is the best thing that will lead you to the solution. So this V becomes, let's see, phi in milliweber. If you put the unit right at the end of the quantity's name, it would give you that indication of what the unit of that number is. So 5 by 1,000, that makes it in milliwebers, right? Which would be 5027, which is the same thing that we got in here. So if you, either way, I would always encourage you to write up all the steps. Obviously, if you do not do the right steps in MATLAB code, you will not get the answer. That's a good thing about it. That makes you certain that you did the problem correctly. We have the magnetomotive force definition. Like in the electric circuits, that you have the voltage source that is the source of basically creating everything in your electric circuit, creating current and voltage and power and everything. In the magnetic circuits, it starts from the sources of magnetomotive force. So magnetomotive force is the source of creating the flux in a magnetic circuit. The term Ni in equation 5H. So where was equation 5H? That was the equation associated with the magnetic field intensity of the solenoid. So that Ni, which is showing the number of turns multiplied by the current, that is called the magnetomotive force, because it kind of shows the bigger that force is, the bigger your H would be in the circuit. The term Ni in the solenoid is called the magnetomotive force, or MMF in summary, shown by the symbol F. So this F-like symbol is showing the magnetomotive force. The severity of the magnetomotive force is an indication of a stronger magnetic field, right? So based on that equation, in I over L, to increase the magnetomotive force, you can either increase the number of turns, or you can increase the current of the ones. The unit of magnetomotive force would be ampere turns. Like the turns doesn't have a unit by itself, but it's kind of an indication that magnetomotive force can be stronger when you increase the number of turns. That's why we call ampere turns as the unit of the SI unit of magnetomotive force. So the magnetomotive force in example 5.1 would be 100, because you had basically 100 number of turns multiplied by 1, which becomes 100 ampere turns. So we said that there is a certain relationship between B, magnetic field density, magnetic flux density, and H, which is magnetic field intensity. And that relationship is through mu, right? If mu is constant, then the relationship between these two will be always like a line. If mu is a constant, the B is mu H, then mu would be the slope of the line that consists H on the horizontal axis and B on the vertical axis, right? That would be the easiest case that you can have. If this is B, this is H, that linear relationship would be coming out of this mu as the slope, which is a tangent of that angle, right? So let's say tangent minus 1 of mu. Is that correct? This angle, whatever angle is, mu times h, right? That angle should be the slope of that curve or that line, which in this case could become arctangent of mu. Is that correct? Yeah. So this happens in the air. In the air, we have the mu 0. So in that case, you have that linear relationship. But in most magnetic materials, the relationship between B and mu is not linear. So it would go based off of a curve, which we call it the BH curve, which is not a simple curve by any means. So here is a sample of a BH curve. So we had, for a solenoid, Ni over L was the H, right? The H associated with the solenoid. And B was mu times Ni over L, or mu H. That was what we had. This mu is not linear based on that curve. How we describe it is that we start from H. Let's say H is changed. Let's say you have a certain number of turns, so N is constant. L is constant. That's associated with the solenoid, right? So we're talking about a solenoid. This has H as the average, L as the average length, and you have a certain number of turns. So both of these are fixed. But let's say your I is not fixed. So you're going to change your I, the current. So this is connected to a source. Let's say you have a sinusoidal source, for example. The sinusoidal source starts from 0 and changes like that. Goes up and down. So let's say it starts from 0 on a sinusoidal wave, goes up, and then comes down to 0 and goes to a minimum, and then repeats that. So what happens if you have the tools to measure basically your H versus basically B? You see that as you're increasing your H, starting from 0, as you're increasing your H, which depends on I, right, the current, then your B increases in through a curve like this path 1. Okay, so look at this path 1. That's when you're starting your I from here to here. You go to a certain value. But suppose you're going to increase the I, so you're going to use another source that goes beyond this I. Let's go like this. You're increasing the I in a sinusoidal fashion. So you're increasing. As you're increasing, you will see that kind of linear up to this point. But after this, as you're increasing the current and you're increasing H, then you see that you get to a kind of a saturation area. So your B will not increase as you expected, like the path in 1 in here. So from this point on, it goes to a saturation, does not increase basically in the same rate that was increased before. So this is path 2. And then, so up to this point, let's say, almost linear. As you're increasing up to this point, your I and H, it goes to saturation. So you get to a saturation, and now you're decreasing your current, right? As you're decreasing your current, you go through, where was I? As you're decreasing your current, then you go through this path, the same path, but as you are further decreasing the current, you don't go back to path 1. You would decrease based on path 3. And as you are even, so let's say this is path 3. And then from here, again, you go to saturation. That becomes basically path 4. And then you're increasing, it goes over path 5. So as you can see, you start from 0, but you don't come back to 0 for your H anymore. So as you're increasing your I and then decreasing it furthermore, you don't come back through the same path, you come back through this. And as you're increasing the current, you go through another path. So this is kind of what you call the hysteresis curve, which is highly nonlinear, as you can see. And every material has its own characteristics and depends on certain basically knee points and certain saturation rates and certain basically characteristics. So this is kind of the BH curve, which could also show through if you have a constant area, that B can translate to phi, right? If you have basically a constant, and that H also can translate into F, because F is Ni, right? And H is Ni over L. So that H and F are dependent on one another. So this hysteresis curve happens mostly in the cases that you have AC currents, because when the current is variable, you see that this is happening. When you change your current up and down, you see that phenomenon. That phenomenon will be existing. And let's say that hysteresis curve would, or hysteresis phenomenon would incur some losses. So that closed loop that you saw is called the hysteresis loop, which will cause some losses in the magnetic core. So in order to better understand why these losses are happening, we need to note that the magnetic materials contain small magnetic regions or domains with magnetic fields of their own. So if you're looking at a certain magnetic material, so there are small regions. Each of these small regions are like small, basically, magnets, which have their N and S poles, right? Small regions of certain basically magnetic fields that are not aligned with one another. They are in different shapes and directions, okay? But when you put this magnetic material under that solenoid tries to basically align all of those areas with one another. So that's been explained here. Under normal conditions, these fields are not necessarily aligned unless they are exposed to an external magnetic field. So that loop, that winding is incurring basically an external magnetic field, which is trying to align all of those magnetic areas together. Hysteresis losses, which we show them by pH, will be associated with the power that is required to align those small magnetic fields or domains in that magnetic core. So we need some external energy so that we can align them together. That would be proportional to the hysteresis loss. If you need more power to align them together, then the hysteresis losses would be more. It can be shown that the hysteresis losses are proportional to the closed area of the hysteresis loop. So if you have a magnetic material like this, that area would be proportional to the hysteresis losses. So if you have, for example, another magnetic material where that hysteresis area is very thin, it means that the hysteresis losses in that magnetic material would be small. All right, so what are magnetic circuits? So a magnetic circuit would be just like an electric circuit, that we require some currents to pass from one point to another point because we need them to be consumed by loads, for example. We need to carry power from a certain point to another point. Same thing is with the magnetic material. So we need a certain flow of magnetic fields to go from one place to another place so that they can interact with the external objects that are there in order to create a motion or generate something. Creating a motion would be, well, when we have a motor, so a combination of magnetic fields and wires that would basically induce a torque on a certain object that would create a torque that becomes basically the motor action, or you have the same interaction between the magnetic materials and wires so that you induce some voltage in a certain winding. That becomes the origination of power generation or voltage basically induction, which would later on become a voltage source or a generator for you. So both of these would require a magnetic circuit. So there are certain quantities in these magnetic circuits that can be, we can have an analogy between them and electric circuits. Same way that we wrote KVL and KCL equations in electric circuits, we can write up with similar equations to KVL and KCL in magnetic circuits, which relate different quantities to one another. So the first element in a magnetic circuit would be a reluctance, which has an analogy with an R or a resistance in an electric circuit. So the reluctance, which is shown with this symbol of R-like symbol, is analogous to the resistance. If the resistance is considered as a characteristic of an electric element which opposes the flow of electric current, reluctance also can be considered as a characteristic of a magnetic material which opposes the flow of magnetic flux. So if you have more reluctance, it means that less magnetic flux can flow through a certain area. If you have less reluctance, it means that more magnetic, basically, field can pass through more magnetic flux can pass through a certain area. Based on this, the reluctance of a magnetic core, if it has a length of L and a cross-sectional area of S, would be equal to L over mu times S. So L is the length of that magnetic material, or average length. Mu would be the permeability, and S would be the cross-sectional area. This would give you the reluctance. If you recall from resistance, what was resistance? Rho L divided by A. So this is the cross-sectional area of the wire. L is the length of the area, and rho is called the resistivity, right? So this was for the electric circuit, and for the reluctance would be L over mu over A. So rho and 1 over L are kind of related to one another between the magnetic circuit and electric circuits. So the SI unit of reluctance would be ampere turn over Weber or Henry inversed. It's good to keep like a table where you can have all the SI units associated with all magnetic field, basically quantity. The Ohm's law or Ohm-like law in the magnetic circuits would be phi is equal to F over R, or magnetomotive force over reluctance that would give you flux. This is similar to Ohm's law, where in the Ohm's law you had I was equal to V over R, right? So instead of I, you have phi, that instead of V, you have your magnetomotive force, F. Instead of R, you have your reluctance. This is the Ohm-like law that you have in the magnetic circuits. Let's see. Figure 5.8 is showing the equivalent circuit of a solenoid. So in the solenoid, you had your basically magnetic core, you had your winding, and it would cause basically a flux. So if you want to equalize it to a magnetic circuit, that would be something like this, that F, or magnetomotive force, that would be N times I. And then you have the reluctance associated with your core. And this F over R would cause your phi, or magnetic flux. So as long as you have one reluctance element, the magnetic flux in that reluctance would be the same, just like the current that flows inside one certain resistance would be the same. So if you have like two sources, this is your, let's say, magnetomotive force of F. Let's say you have reluctance 1, reluctance 2. These are associated with two different, basically, magnetic materials. Then you have phi 1, phi 2. You just go to each of these reluctances, and then the total phi would be equal to phi 1 plus phi 2, just like the electric circuits. So there's an analogy between a magnetic circuit and an electric circuit, as you can see. We have the permeance, which is analogous to conductance in electric circuits. Conductance would be 1 over resistance, and permeance would be 1 over reluctance. And its SI unit is Henry, because the SI unit of reluctance was Henry minus 1. So this becomes Henry. Let's go over the inductance also. The inductance of a certain reluctance would be equal to N squared over that reluctance. Where if you have a winding and a certain reluctance where the winding is wrapped on, then N squared over that reluctance would be equal to V inductance. And the unit of inductance would be the same as the unit of permeance. The unit of permeance is Henry, so the unit of inductance would also be Henry. All right, so there is an example here, reluctance and inductance. So if we want to find out the reluctance of the core and the inductance of the solenoid in the previous example, you have your reluctance equal to L over mu times S. This would become Henry minus 1, right? Or ampere turns over Weber. So let's just use mu 0 times mu R. And then L would be N squared over R, would be in Henry's, right? But that becomes this much in Henry's. Or if you want to do that in millihenries, You would just multiply L by 1,000 to become independence. The next law would be the Faraday's law and its relationship with the flux linkage. So based on the Faraday's law, when a coil or winding is exposed to a time-varying field, so if you have a field in this space that is time-varying, when you expose that winding to that time-varying field, a voltage would need to be induced across the terminals of that coil, which would be proportional to the rate of change of the magnetic flux. So you have a field, it has a magnetic flux. Field is changing over time, which means that your magnetic flux is changing over time. The rate of changes of that magnetic flux over time would be proportional to the voltage that would be induced on your coil. So for a coil with n similar turns of wire, just like the one that we saw in the solenoid, the Faraday's law can be written as n d phi over dt. So E induced, the voltage that it induced on that coil would be n times d phi over dt. And we call that n times phi as the lambda, which is called flux linkage. So phi is flux, d phi is the changes of flux, d lambda is the changes of flux linkage. And that flux linkage would be n times phi. So lambda, which is n times phi is called the flux linkage, which is considered as the extension of the magnetic flux, which is linking the flow of magnetic flux with the turns of the conductors. So the SI unit of the flux linkage would be Weber turn. The flux linkage, the flux itself, the unit of flux was Weber. But since flux linkage is phi times n, in order to show that n is important, the number of turns is important in increasing the flux, although turn doesn't have any unit by itself, but we call it Weber turn to show that this is the nature of this is flux linkage, not the flux itself. Flux times the number of turns. That makes sense. We have a law here called the Lenz's law. So we talked about this coil, this varying magnetic field around this coil. The rate of this magnetic field around this coil, the rate of change over time will induce some voltage on your coil, which would be depending on the rates of change of flux linkage over time, right? Now, that magnetic coil itself, if there is a voltage induced in it, and if it is closed, so if I basically connect the two sides of the terminal so that I have a current flowing in that point because of that. So voltage doesn't cause current by itself unless there is a path, a closed path, right? If I close the path, there would be a current flowing in that point. That current itself would make another magnetic field, right? So I have an originating magnetic field that induced voltage on my coil. Because I closed my coil, there will be a current in my coil that will produce its own magnetic field. Okay? So based on Lenz's law, it says that the polarity of the voltage that is induced on my coil should be in such a way that if there is a current flowing in the coil, it would oppose the changes of that originating magnetic flux, right? So my originating magnetic flux is changing over time, goes up and down over time. So the current that will flow in my coil will create another magnetic field, which will be time varying, and its time variation would be opposing, trying to oppose. So if this one is going up, the opposing magnetic field should be in a way that it goes down. It tries to cancel it, right? If you want to make an analogy like an inertia in mechanical system, if you try to basically put a force, then the inertia would be in a way that opposes that force, right? So same type of thing. If you're creating a magnetic flux, if you're creating a voltage in a field, that should result in a magnetic flux that opposes the originating magnetic flux. Does that make sense? So that's called the Lenz's law. So the polarity of the induced voltage must be such that if current flows in that coil, it creates a magnetic field which opposes the changes of its originating magnetic field. Now, let's go to eddy currents. When a magnetic core is exposed to a time-varying field, voltage would be induced in it based on Faraday's law. Right? We talked about a coil and a time-varying magnetic field. We said that that time-varying magnetic field will induce a voltage in this coil, right? Now, instead of the coil, let's consider the magnetic material itself. So we have a few things in here. So here is my magnetic core. This is my coil. Let's say there is like a time-varying magnetic field. That time-varying magnetic field will result in some voltage here, right? Now, the same way that the voltage is induced in this winding, because most of my magnetic materials are conductors of electricity themselves. So we would have like certain areas, certain loops here where voltage is induced on them. And because I have the conducting material inside my magnetic material, it would cause us some losses. This loss is different from hysteresis losses. Hysteresis losses was not because of conduction, right? It was because of creating a force to align the internal magnetic areas with the external magnetic field. But this loss is associated with the currents that flow in basically internal areas of my magnetic material because of current conduction. There is electric current directly existing, like loops of electric current are existing inside my magnetic material. That causes some losses, which we call the eddy current losses. So that's a different type of loss. These currents are called eddy current losses, which warm up the magnetic core. When the originating magnetic field is periodic, so usually you have magnetic fields that are changing like a sinusoidal, in a sinusoidal way. The eddy current losses would be a nonlinear function of the frequency. So frequency of that magnetic flux. If that magnetic flux is sinusoidal, has a 60 hertz frequency, then we have a certain basically eddy current. If it becomes 70 hertz, eddy currents would be different. There would be a relationship between the frequency of that originating magnetic flux and the eddy current losses, which depends on the magnetic material. And it in general is a nonlinear function of the frequency. Keep that in mind.